Have you ever looked at a diamond and wondered why it sparkles so brilliantly? Or noticed a mirage on a hot road that looks like water but disappears when you get closer? Both of these magical effects are actually due to a single phenomenon in physics called total internal reflection. Now, imagine a beam of light moving from a denser medium, like glass, into a rarer medium, like air. Usually, the light bends away from the normal. But something fascinating happens when the incident angle is increased. At a certain special angle, known as the critical angle, the refracted ray just skims along the boundary. And if we push the angle further, the refracted ray disappears entirely, and the light bounces back fully into the denser medium as if the boundary had turned into a perfect mirror. This complete reflection inside the denser medium is what we call total internal reflection. Let's now dig a little deeper. What exactly decides this critical angle? The answer lies in the refractive indices of the two media. Mathematically, we define it as sin c equals nu2 divided by nu1, where nu1 is the refractive index of the denser medium and nu2 is that of the rarer medium. But there are two more fascinating influences. First is the wavelength of light. Violet light, with its smaller wavelength, has a higher refractive index. That means its critical angle is smaller. Red light, on the other hand, with its larger wavelength, has a lower refractive index, and so its critical angle is larger. That's why we say the critical angle increases with wavelength. The second factor is temperature. As temperature increases, the density of a medium decreases, which reduces its refractive index. And from our relation, mu equals 1 over sin c, this lower mu leads to a larger critical angle. For instance, in water, the critical angle with air is about 49 degrees. But in diamond, the critical angle is just 24 degrees. And that's the secret behind the diamond's sparkling brilliance. Light gets trapped inside, bouncing multiple times, before finally escaping. Now, when does this dramatic reflection actually occur? There are two strict conditions. First, light must travel from a denser medium into a rarer medium. That's non-negotiable. Second, the angle of incidence inside the denser medium must be greater than the critical angle. Only when these two conditions are satisfied does the ray stop refracting out and instead bounce back completely. In this case, no light energy is lost into the rarer medium. Unlike ordinary reflection, where some energy is always absorbed, here almost 100% of the light is reflected, just like a perfect mirror. Let's visualize how the ray behaves at different incident angles. Case 1. If the incident angle is less than the critical angle, the ray partly refracts into the rarer medium and partly reflects back. Case 2. When the incident angle is exactly equal to the critical angle, the refracted ray doesn't leave the surface normally. Instead, it travels right along the boundary at 90 degrees. Case 3. If the incident angle exceeds the critical angle, then the magic happens. There is no refraction at all, and the ray is completely reflected back inside the denser medium. This smooth transition from partial refraction to total reflection is beautifully shown in the ray diagrams you see here. Now, why is this phenomenon so important? Let's look at some fascinating applications. The most revolutionary is in optical fibers. Here, light signals travel through a thin glass core, bouncing back and forth entirely by total internal reflection, carrying internet and phone data across continents. Next, diamonds sparkle because their very small critical angle of about 24 degrees ensures that light entering a diamond undergoes multiple total reflections before emerging, creating brilliance. Then there's the phenomenon of mirages. On a hot day, the air near the ground is less dense than the air above. Light from the sky bends and eventually undergoes total internal reflection, making the ground appear like shimmering water. Finally, prisms and instruments like periscopes, binoculars, and cameras use total internal reflection to reflect light exactly by 90 or 180 degrees, giving us sharp, distortion-free images without using silvered mirrors. Clearly, total internal reflection isn't just a textbook idea, it's a principle shaping both nature and technology. Let's test our understanding with a numerical example. Suppose a ray of light travels from glass with refractive index equal to 1.5 into air. We are asked to find the critical angle and to check if total internal reflection will occur when the angle of incidence is 50 degrees. Step 1. Recall the formula sin C equals mu2 over mu1. Here, mu2 is 1, mu1 is 1.5. So, sin C equals 1 divided by 1.5, which equals 0.667. Step 2. Now take the inverse sign. So, C equals sine inverse of 0.667, which comes out to approximately 41.8 degrees. Step 3. Compare this with the given angle of incidence, which is 50 degrees. Since 50 degrees is greater than the critical angle of 41.8 degrees, the condition for total internal reflection is satisfied. Therefore, the ray will undergo complete internal reflection and no refraction will occur. This simple example demonstrates exactly how the concept and the formula work in practical situations. So, let's quickly revise what we've learned today. Total internal reflection is the complete reflection of light inside a denser medium, happening only when light goes from denser to rarer and the incidence angle exceeds the critical angle. The critical angle itself depends on the refractive indices of the media, the wavelength of light, and even temperature. Depending on the incident angle, light may refract, graze the boundary, or reflect totally back. And as we've seen, this single principle explains dazzling diamonds, fast internet through optical fibers, desert mirages, and sharp reflections in optical instruments. I hope now you can see how this elegant principle of physics, total internal reflection, connects both the beauty of nature and the technology of modern life. See you in the next session with another fascinating concept of light.